Section 12.1 talks about three-dimensional coordinate systems. Chapter 12 in general is going to talk about everything that we did from 1 and 2 dimensions transferred to 3 dimensions. So, if I was talking about 1 dimension, 2 dimension, and 3 dimension, I'll talk about that briefly. If this is 2 dimensions, 1 dimension, if this is 0, I would go to 3, and pretty much the location is right there. Two dimensions. If I'm talking about x equals 3, there is the x-axis. I would move identically to what I just did, 1, 2, 3, and I'll mark that point, except now you have this y that they never mentioned. Well, if x equals 3, this point is actually 3, 0. Y could also be 1, y could also be 2, y could be 3, y could be -1, -2. If I want to trace all of these points, that's where the vertical line comes from. Now, I know that you know x equals 3 is a vertical line. You need to grasp the concept behind it so 3D comes in naturally or easier to grasp. Now, for some reason, mathematicians decided to switch the x-axis. The y becomes where the x is, and where the y was, they called that a z. If you took engineering physics, you would know that this is not the case. In physics, they left this as x, this as y, and they called this axis a z. So here you have to adapt a bit because the entire chapter, the entire course is built on this. So when I say x equals 3, you would say, well, let's get to that point. On the x-axis, 1, 2, 3. Now, a couple of issues. If you talk about a point in 3D, you're talking about x, y, and z. 2D, x and y. 1D, just x. So that's important. X, y, and z. You notice here there's only x equals 3. There's the y. Y could be 1 is really 1 to the right. Y equal 2 is really 2 to the right. Again, there's 1, there's 2. And by the way, if you get the 2 dimensions, and what you do, you add a third axis. You think of it as coming out of the paper. That's the x. And if you want to mark points kind of parallel to the original x and parallel to the new axis, that's really how you mark points. We'll get the hang of this. So y equal -1 is actually right there. So if you mark it, it's right there. You notice that's the line referring to x equal 3, except there is no z either. Z could be 1, there's z equal 1, z equal 2, and x could be 1. So what you end up getting is a plane perpendicular to the y-z plane, and this one's infinite. I'll be drawing a bit more of those and we'll get the hang of this. There's a lot of graphing in this chapter, and in the beginning it seems to be messy. It'll get better. So let's get a point out of the way. If I want to talk a simple point 2, 3, I know you know how to plot 2, 3. I need you to bear with me and entertain me a bit. 1, 2, that's what you do. If you graph, I have the whole thing in front of me. X equal 2, y equal 3, since you're fixing x to be 2 and y equal 3, where these two lines meet, that point right there, so you end up creating this rectangle. Oops, that's way too thick. if you really think about it, that's where the rectangular coordinate system comes from. Those rectangles. And all of this work is just to pinpoint that one point. If I want to talk about 3D, if I want x to equal 2, I'll move along the axis 1, 2, and I'll draw a line. Y equal 3, 1, 2, 3, and I'll draw a line just like I did. So, in a sense, what I just created, oh, it's very hard, I just forgot, it's very hard to do. It's not going to work either. I know. That right there is literally mimicking this right here. But there is an added point. Z equal 4. 1, 2, 3, 4. Now if you go to this point right here and you go up 1, 2, 3, 4. You end up creating a rectangular prism. And guess what? This point is actually right there. If you really look at it, you're moving 2 in the x, 3 in the y, and 4 in the z. And that's really how you get just one single point. So, we have tons of examples to go through to really see how this works, and not to worry if you're not seeing it. We'll play with that. A couple of equations we have in this section, one for a distance and one for a sphere. If you talk about a sphere, it looks pretty much like a circle. X minus x naught squared, y minus y naught squared. You add an extra component, which is z minus z naught squared, equal r squared. The center is x sub 0, y sub 0, z sub 0, and the radius is square root of that number. So, if I look at what this is a system of equations. This says x equal 3. Okay, well, x equal 3, 1, 2, 3. I could be anywhere along this line or this line because there's no z yet. So keep that in mind. So far I'm fixed. Z equals 0, that means you really do not go up or come down. You stay on the floor. Z equals 0 is all of this ground. So you're stuck, you're not moving up or down. But do you notice they didn't give us a y, there's no y? Since there's no y, this is really gonna stretch in the y direction, left and right. Of course, it looks a lot nicer. But, you know, since you don't have this tool on your homework, you could just graph it by hand. That's not a problem. As long as you label 3 units, I know what you're talking about. If you want to rescale it, you have to tell me what that is. If I look at example B, now, by the way, everything that I'm doing here matches your homework. Every problem that I do in this lecture, you will find homework identical to that. When I say here I want x to be 3, I'm still fixed at x equals 3. So I'm fixed at this line. But I could go up or down. But then they fixed y to be at 1. Y to be at 1. Now I'm tied to this point. But you notice there's no z. If there is no z, that means this z could be 1, z could be 2, z could be 3, negative 1, negative 2. What you end up with, a line that's parallel to the z-axis, in which that's 1 unit and that's 3 units. And what if I talked about a sphere with a radius of 3? Well, it's kind of messy in 3D, but let's try. You move in the x direction, 3 to the right, 3 to the left. In the y direction, 3 to the left, 3 to the right, connect that, and it's going to take you some time to adjust. And then z equal 3 up and 3 down. You'll notice it's very hard to graph if you scale it first. This is really how I graph it. This is very challenging, so this is what I do. If I want to graph that, I would go ahead and sketch a circle. And what I'll do, and another, and then I'll add the axis in it. I'll draw the x, y, and z. That's the easiest way for me to graph a sphere, except I really need to adjust, so I would go ahead now and say there and there, in which this is 3 units. Oh, I missed the forward. There we go. The front is 3 units and the back is 3 units. There we go. Again, it's going to take some time for you to adjust. The back doesn't look right. There we go. Much better. So a sphere is kind of annoying to do, but you do your best. Now, this is, remember, always a system of equations. This is a circle. I know that. There's the x, there's the y. It is a circle. Normally, traditionally, I would move 3 in all directions. There it is. Except they're fixing z to equal 2. So you're going to go to z equal 2, and from that point, you're going to move 3 to the right, 3 to the left, 3 forward, 3 backwards. So that circle is tied to z equal 2. You go up 2 units up, and you have a flat circle. Here, I have a circle in the x, z plane, but y equals 0, that means you start at the origin, because you don't move right or left because that's the y-axis, so you move up 2, down 2, to the right 2, and to the left 2. You'll notice if you want to get a good circle, you have to really make the x-axis a bit smaller than the others, the y and the z. And here, if they gave me a sphere and z equal 1, well, they're saying two things. A couple of ways I could do this. I could think of it as a graph a sphere, oh boy, okay, this is going to be tough. I could think of it as a graph a sphere, see, that's how I normally graph it. It's a lot easier this way. And z equal 1, don't you go up 1 unit and you're going to stretch a plane in all directions? You're looking for this and this, meaning the intersection. Isn't the intersection a circle right there? You can get a much better result. And when we meet in class, I could show you some examples like that. I'll go to GeoAlgebra and show you there. That would mean you could say it is x squared plus y squared, and if you plug z in, because that's how we solve systems of equations, right? I'm looking at x squared plus y squared equal a 9. I know how to do that. That's a circle, right, in the x, y plane, except z is fixed to be 1, kind of like this. You go up 1 unit, and you move 3 units to the right, 3 units to the left, 3 units backwards, forward, and this is really the intersection of those. Think of it this way. You have an orange, and you slice z equal 1, you go up 1 unit, and you slice with a knife, and you're trying to see, if I look from the top, what do I see? I only see this surrounding. And it's only the shell because it's equal, so it's the surrounding, not the solid. The solid's coming up later on. What do you think this would be? Well, this is identical to what we just did. If you really throw the 1 in, you're looking at x plus 3 squared plus y squared plus 1 squared equal 10. It's really x plus 3 squared plus y squared equal a 9. So I'm fixing z to be at 1, and I'm fixing x to be at negative 3. And from that point, I'm going to move 3 in the x and 3 in the y, and my circle is going to be tangent to the z-axis. It's going to be parallel to the x-y plane. So this first assignment is going to be a bit confusing till you get the hang of this. Not to worry, I could work that with you as well. And here, if you look at this sphere, we know how that looks, right? But z equal y. There's the y, there's the z. Anytime you want to transform that, that's like y equal x in 2 dimensions. Isn't that a line cutting at 45 degrees? If I have a plane cutting at 45 degrees, and I have a sphere, imagine you have an orange, right, or a soccer ball, and you slice at 45 degrees, and you turn it and you're looking at it. What do you see? Well, guess what? There's a quick way you could do that. If you take y and put it in place of z, that would say x squared plus y squared plus y squared equal a 9. That's x squared plus 2y squared equal a 9. That's really x squared over 9 plus y squared over 9 halves equal a 1. That's really an ellipse. If you really think about it, you would move 3 in the x, you would move 3 over radical 2 in the y, right? And you will that's really what you're looking at. But it's really along this line, and let me elaborate now. It's really along the line. I need more space. I'm running out. Okay. I could do this. Kind of hard to see. It is a sphere. And you're cutting at 45 degrees. Do you see that? There it is. Except this is not really on the ground. It's really lifted up. You have a homework problem like that, and I'll elaborate more on that. I'll use GeoAlgebra. It's a good place to be at. And if you sketch a graph of this and this, you'll see the overlap. I will show more about that once you get to the homework. There aren't that many of those for now. They come up much later. Well, let's see how this works. How about here? I have y fixed at 3 and there's no y in there. 1, 2, 3. And isn't this a parabola wrapped around the z-axis? And it's going to open. So a regular parabola opens like this, except this one is fixed at 3. And there it is. Alright. Again, I'll talk more about these kind of graphs. There's only a couple of them in this homework. When we cut back to them, I'll go in GeoAlgebra with you and we talk about that fully. Distance in 3 dimensions is very close to what you know in the traditional class. It is given 2 points, ignore the z, x1, y1, x2, y2, x2 minus x1 squared plus y2 minus y1 squared, and you add the z component, and if I want the distance between those 2 points, then the distance is the square root of negative 1 minus 2 squared plus 1 minus 3 squared, and you add the z components. And the distance would be the square root of 3 squared is a 9, negative 2 squared is a 4, 1 squared is a 1. There it is. Now, I'm picking what we need for this class. There's a lot more, but I'm only going by what we need. If you look at the point 2, 3, 4, I would suggest that you sketch a graph every time you're looking at one of those. The point 2, 1, 2. So this runs back and forth, but y is fixed at 3. 1, 2, 3. I know we did that already. And z is fixed at 4. So if I go up 4 on all ends, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. You're really looking at this one specific point. There it is. Now just, again, in this class you're going to have to visualize a lot. In this chapter, you kind of have to guess, but since in chapter 13, 14, 15, and 16 we sketched those over and over, you'll get the hang of how this works. So you'll notice these are my 2 units in the x, these are my 3 units in the y, and these are my 4 units in the z. Well, describe the set of points through this point perpendicular to the x-axis. If I want this to be perpendicular to the x-axis, what do you think that's going to look like? Well, perpendicular to the x-axis, isn't that going to be perpendicular to the x-axis? What's the equation for that? Isn't that x equal to, if I said sketch x equal 2 with no y and z, well, guess what? That would be perpendicular to the x-axis for sure. And how about the y? Well, if I want it to be perpendicular to the y-axis, isn't y equal 3 perpendicular to the y-axis? Think of it as like those laser pointers. You are standing at this point, and if you put your pointer in this direction, wouldn't that be perpendicular to the y-axis for sure? It's really perpendicular to the yz plane, right? But that would be the line. I could have a plane, but a line will do. Actually, when you say y equal 3, yeah, x and z could be, that is an actual plane. Because x equal 2, x equal 2, it really looks like this. I should start that way. X equal 2, there's no y and there's no z. That plane right there, I shouldn't hold on. I was going to hold on until much later to discuss this, but let's get out of the way. X equal 2 is actually a plane that is perpendicular to the x-axis on all fronts. When I say y equal 3, do you notice there is no z and there is no x? So if I really looked at the graph of one grid, if I really looked at the graph of y equal 3, that is go 1, 2, 3, that really looks like this. pretty much this would be, oops, pretty much this would be this. That's an infinite plane, by the way, that's running, never ending, in all directions. But isn't that perpendicular to the y-axis? That's for sure. Or y-z plane if you want, it doesn't really matter. And obviously z-axis, that would be z equal 4. And again, for practice purposes, if I said sketch a graph of z equal 4, 1, 2, 3, 4, you run along the x, along the y, it's really a plane. So that's like the roof of a room. That's really right there. And that would be perpendicular to the actual z-axis. It's perpendicular to more than that. It's really perpendicular to the z x plane, but that's sufficient. The homework will be listed on this PDF at the end of it. I don't include that in the videos because this is going to be used for all of my third semester's calculus classes in all of my schools. So the homework will be listed on this PDF that I'm going to provide in the website.